This is a particle filter question. Suppose we are involved with 4 states. In these 2 states over here, we tend to observe A, probability 80%. Probability 20%, we observe B. In these 2 states, we tend to observe B with 80% probability, and with 20% probability, we observe A. Suppose we have 3 particles, one over here, one over here, and one over here, and we observe A. Let's call this particle over here particle A, lower caps A, lower caps B, lower caps C. What is the probability that we sample A, given that we just observed A, which means we're more likely to be in one of those states, 2 states over here? What's the probability of sampling B? What's the probability of sampling C? The particle A will get an importance weight of 0.8, non-normalized. You have to normalize in a second. Particle B will get an importance rate of 0.2, same for particle C. If we add those together, we get 1.2. Therefore, we have to divide everything by 1.2, which gives us 2/3 for the probability of sampling A, and 1/6 each for B or C. This is another particle filter question. Now we're looking at the state transition. We're given the same state space as before and the same 3 particles, one over here, one over here, one over here. And to give the states names, you're going to call this one A1, A2, B1, and B2. Let's assume we take a single random particle with uniform distribution and we emulate a next state. The state transition works as follows. A particle will move with probability 1 to an adjacent state, where adjacent is either north, south, east, or west, but not diagonal. And because every particle has 2 adjacent states, it'll break ties at random. So we're going to pick one of the 2 with 50% probability. So for this one particle that we've drawn at random and it does a random state transition, what's the probability it finds itself in A1, A2, B1, and B2? If you look at the chances of the particles that can end up in A1, we find that only this particle can go up here. So let's call this a 1. To A2, there's 2 particles that can go there. Let's call this a 2. There's 2 particles that can end up in B1. This one and this guy over here. Again, a 2. And 1 that can make it into B2. Now this is a total of 6. If we normalize so you get extra probabilities, then A1 is worth 1/6. A2 1/3, which is 2/6. B1 again 1/3. And B2 is 1/6. So here's a multiple choice question for particle filters. Say we implement a particle filter, such as in robot localization, and we use exactly 1 particle. Which one of the following statements are true? Check any or all of the following statements. Measurements will be ignored. Check this box if you believe that's the case. The result is generally poor. It cannot represent multimodal distributions. The initial state, if known, is ignored. And the state transitions are ignored. If none of the above applies, check the final box down here. And the answer is measurements are indeed ignored, which has to do with the following. We do weigh particles by the measurement probability, but we normalize them to 1. And if there's only 1 particle, it will always normalize itself back to 1, so the measurement probability has no effect. The results are generally poor. That is, a single particle is just insufficient to do anything interesting. So this is absolutely the correct answer over here. Clearly, a single particle cannot represent a multimodal distribution, so it has multiple modes, like something like this over here, because it's just 1 particle, so this is actually correct. The initial state, if known, is not necessarily ignored. You might actually place the particle at the initial state, and it might consider it in the filtering result. The state transitions are also not ignored, because you will still propagate this particle forward according to the state transition, and because 3 of them are true, the final one isn't. Another particle filter question. Check the following statements if they're true. They're usually easy to implement. They scale quadratically with the dimensionality of the state space, and they can only be applied to discrete state spaces. Finally, if none of those applies, check the final check mark over here. And only the first answer is correct. They are usually easy to implement compared to any other filter. They do not scale quadratically. In fact, normally they scale exponentially with the dimensioning of the state space because you need exponentially many particles to fill out the state space. The filter that scales quadratically is called a Kalman filter, but we didn't really talk about it in this class. They can only be applied to discrete state spaces. Is clearly wrong. We saw how to apply them to robot localization, which is a continuous or real value state space. And because this first one is true, the last one, none of the above, is clearly false.